Hello everyone, my name is Titus Dutton and I'm here for project 2 of CpE 3110. Right now I'm going to go ahead and start off with my 3-bit signed adder. Here is the code for that, showing that we have two 3-bit inputs, 3-bit output, an overflow register, and this is all of the what's the word I'm looking for here? Logic for it all. Basically saying that if the top bit of A is 0, the top bit of B is 0, but the top bit of the output is 1, then there's an overflow, and then vice versa. And then we can see the wave for this, where if we have 1 added to 3, then we magically get a -4, which triggers that overflow. And all of the other instances, the -1 plus a -2 is our -3, 2 plus 2 is -4, that triggers overflow, 1 plus 1 is 2, no overflow. We can go ahead and move over to Quartus, and we can see that this is the block diagram that we're using to hardware test it. So 2 3-bit inputs, output to show timing, the oscilloscope output, lights output, the overflow output. All same as the previous project, and then if we run our, let's see, where was it? Is it this? Yes. Okay, if we run our RTL viewers, then we can see what Quartus thinks it should look like. And it's showing that we have an adder here with AND gates and OR gates, basically just simple Boolean for our overflow and outputs. And we can go ahead and move over to the test bench, showing that if we have 1 and then we add 1 to it, then it's 2. 1 plus 3, or 1 plus 2, or, yeah, no, 1 plus 3 is 4. And then if we were to add 1 more to it, this would end up being -3. But if we want to trigger the overflow, then this light kicks on, showing that we have a -3 plus a -3, so then that would trigger that. Moving over here, we have our oscilloscope showing a time delay of 30 nanoseconds. And that's everything for this circuit. Okay, for the next circuit in this project, we have a 4-bit signed shift left. So as you can see, we have a 4-bit input and we have a 4-bit output. We also have a clear control for this one, and an assignment saying that if clear is high, then all of the bits will be 0, else it will just function as normal. And over here in the signed, we can see that if we take a 1 right here and we shift to left 2, then we get, with our clear high, then we get nothing. If we have a 2 and then we shift to left 2, then we get -8. And if we have a 4 and we shift to left 2, then we get nothing, but this is also with the clear. With our -8, if we shift to left 2, we get 0, and so on and so forth. If we move over to Quartus, then we can see the block diagram that we're using for this, where we have the clear input, the 4-bit input, the 4-bit output for lights, the oscilloscope, and then the 4-bit output so that we can compare for timing. And if I go ahead and compile this so that we can see the RTL, we go to Tools and then Netlist Viewers and RTL Viewer, then what it's saying is it's pretty much just, it's using a mux, and it has a clear as the select line. So a fairly simple circuit. And if we go over here and we have our, let's say we have our clear high. Any input does nothing. None of our inputs will do anything. But if our clear is low, then if we have 1, we shift to left 2, then it does nothing. If we have our -8, we shift to left 2, it's nothing. If we have a 2 and we shift to left 2, then it becomes our -8 right here. So as we can see, the 1 to 4, that's working. And then if we move over here to our oscilloscope, we can see the time delay is that of 60 nanoseconds. And that's going to be it for the circuit. For the third circuit of this project, we have an unsigned shift right 2, where we have a, if it'll focus, a 4-bit input and a 4-bit output, where the assign is simply just F is equal to A shifted to the right 2. So nothing super complicated here. And then if we move over to our wave diagram, we can see that if it's 1 and it's shifted right 2, it's 0. If it's 2, it's shifted right 2, it's 0. If it's 4 and it's shifted right 2, then it's 1. In this instance, we have, oh, that's fun. Yes, we have a 4 shifted right 2, and then that is 2. And then we have 3 shifted right 2, it's nothing, so on and so forth. And if we move over to Cordis, then we can see this is the block diagram that we're using, where we have a 4-bit input and a 4-bit output for the oscilloscope and for the LEDs, and then the input as an output so that we can determine the time delay. And if we move over to, which it should be compiled correctly, if I go to netlist viewers and RTL viewer, then we can see this is what Cordis thinks it looks like. It is just an input wired to an output, and it is doing some internal computation that it is probably not showing us. If we move over here to the hardware testing, then we can see that 1 bit of info does nothing, 2 does nothing, but if we have 4, then we have 1. And if we take it up a notch, we have 2. So this is working as desired. And if we move over here, we can see that the oscilloscope has determined a time delay of 2 nanoseconds. And that is going to be everything for the circuit. Hello, this is the next video, the next circuit in the project. And for this one, we have a rotate carry 2, where what's happening here is we have a 4-bit input, a carry in, a carry out. We also have a 0 flag for this circuit and a 4-bit output. In the code, I've kind of just put my little mental track here. So we have, we're using an array for the assignment where the first 4 pieces of information are F, the last piece of information is the C out, and we're using a always block for the Z flag, seeing if all of the bits in F are 0, if so the Z flag triggers. For this case, what's happening is we have all of these inputs, and then we have our Cin input, which we can decide up here as a secondary input. The first rotation will take the C input and bring it to the front of the F values, and then once again we shift right again and it will take it to the second, and all of the pieces of information will rotate respectively. For our waveform, we have right here, we have 1 where it shifts right 2, which then it moves that 1 to the front, and you can see that the, let's see if I can make this look a little prettier. There we go. So the Cin is low and the C out is low. But if we have a 0010 right here, if it shifts right 2, what ends up happening to this piece of information is it goes into the carry out. So it's in the carry bit. And then we also had a carry in where that is going from where the carry out bit would be held, shifted right 2 into the 3rd position of the F output. And then more examples represent that down here. Moving down to Cordis, this is the block diagram where we have a 4-bit input, our C input, our C output, our Z flag output, the output for lights and the output for the oscilloscope, and then the input as an output to determine time delay. And if we go to tools, we can see what the RTL viewer thinks this should look like. Which right here we have our 4-bit input, the C input, and then we have an equal right here with our Z flag, our F out, and our C out. So quite the little mess. And if we move here, we can see that, let's see what's happening here. So this is our Z flag showing that all of these main 4 lights are going to be our pieces of information. If we have 1, we shift it right 2, then it goes into the 3rd position. Then this goes into the top position. And if we have 3 and it shifts right 2, then we can see that the 4 pieces of information that we're looking for are all low. So our Z is high and our carryout is high because our third bit of information got shifted right 2 and is now in the carryout. If we move over to the oscilloscope, we can see that the time delay for this circuit is going to be 12 nanoseconds. And that is everything for the circuit. For the next circuit in this project, we have a shift left in where we have a 4-bit input, a 2-bit shift, a 4-bit output, and then we have an overflow flag and a 0 flag. So what I'm doing here is I'm assigning the F full is equal to the A being shifted an N number of amounts, and the output that we're actually looking at, what is being visualized, is it would be the 0th to the 3rd bit. And for the 0 flag, we're using an always block showing that if any of the bits, if all of the bits in our final output are 0, then the 0 flag will trigger. If not, and then the overflow flag is saying that if any of the top bits that are not being shown in the F, that are included in the F full, are 1, then the overflow will trigger. And we can see that in the waveform, which this one is a little bit messy, we have 0, 1, 0, 0, and it's being shifted left 1, where there's going to be no overflow, no 0 flag. And we can see right here that the output is 1 followed by 3 zeros. And then for the F full, there's 3 bits leading on it. For this one, it's the, we have an input of the same, but this time we're shifting it to the left 2. So we can see that the overflow kicks and the 0 flag kicks because one of the bits in the top 3 pieces of information for the F full is high, and all of the outputs for what we're measuring is low. And then there are more examples here. Moving to the hardware test, we can see that now the Altera board is being silly and it's throwing a bunch of random LEDs that aren't set for anything, so ignore that. But this LED is showing that this is our 0 flag. It's showing that there's nothing going on here. Now if we have our main bit high and we shift it to the left 1, we can see the 0 flag and the overflow flag both kick. If we shift it 2, it does nothing because we're not rotating. But if we have a 2 for our information, we shift it 1, then we shift it 2, and then if we shift it 3, and then that kicks all of our flags. Over here on the oscilloscope, we can see that we have 28 nanoseconds of time delay. And that's going to be everything for this circuit, but I'm lying because I have not shown you the block or the RTL. So this is the block right here where we have a 4-bit input, 2-bit shift input. We have our F output, the F full, the overflow, and the 0 flag outputs, the oscilloscope output, and then the input as an output to determine time delay. And assuming that I'm gonna go ahead and just recompile this just to make sure that we get the correct RTL. And RTL viewer, and this is what Cordis believes it ought to look like. So we have a shift here, and then we have an OR with the top 3 bits for the overflow. We have our 0 flag, our F full, and then our main F output, and these are just buses pulling specific pieces of information. And now this will be all for the circuit. Okay, and for the final circuit of this project, we have a D flip-flop that functions on the negative clock edge. So we have our input D, our output G, and then our clear input, pre-input, and then our clock input. And we're using an always block saying that on the negative edge of the clock, the positive edge of the preset, or the positive edge of the clear, this always block will then activate, and it's saying that if pre is high, then our output will be high. If else, if the clear is high, then our output is low, else our input is equal to our output. So nothing too crazy here. Moving over here, you can see that, and I'll move this so you can see values changing. For here we have our D is 0, but this changes to, what ends up happening is our input is 1, but our output is still 0. And then on the negative clock edge right here, you can see that the output changes to a high output. Here you can see the preset is high, even though the output is low, so our preset's working. and then our clear is also working, because regardless of where the clock edge is, our clear is swiping it down to 0. And then over here, we can go ahead and I believe this is our pre, so this will set this high, and I can drop it and move to the next clock cycle. And then this is our input, so then we'll move to the next clock cycle and we can see it runs high, and then we can go ahead and clear that off. So we can see that this is working correctly, because if we set this high, then press this, then set it low, and then press it again, the output changes. So we have a D flip-flop. Moving back over here, we can go to Quartus and we can see this is what we're working with. So we have our D input, all of our settings, so our clear, our clock, our preset, the output oscilloscope, and then the input as an output, which I had to set this to the pre, because since this is a clock-based circuit, I would have to press this secondary button after pressing the switch to get these two waveforms to change at the same time, which created extra delay. So I set it so the switch changes with the value and I don't have to hit the clock for it, so I can get an accurate time delay reading. And then for the RTL, it gave us something fun. It just gave us a negative D flip-flop with all of our inputs and our preset and our clear. So it knows what's going on, thankfully. And if we move over to the oscilloscope again, we can see that this one has a time delay of 92 nanoseconds. And that's going to be everything for this circuit.